Yeah, the title of my talk is Trustworthy AI Under Real World Data Challenges. So, uh, yeah, these are the kind of like three broad pillars of AI right now. So, you need data, you need annotations or labels for that data, and you train a model, and the model, acquires some knowledge based on the kind of data you train it on, right? But in my research at Hopkins, I target, the problem of, in the real world, things are messy. So what if one of these three players is missing or corrupted, right? So for example, like let's say you don't have labels in your data, or you don't have complete labels, or you have corrupted labels. So this is one of my works. I'll be discussing two works in this talk. So the first work targets the missing labels problem, and it is titled TOGA, Temporally Grounded Open-Ended Video Question Answering with Weak Supervision. So yeah, this work was done in as collaboration, like as a collaboration between Hopkins and SRI during my internship, and first published at ICCV last year. So for this work, we focus on the problem of video question answering, as the title suggests. Um, we want to generate open-ended question answers, like we don't need any answer choices. We want to generate like natural language English words rather than just like A, B, C, D options. And we want, the theme of following the theme of trustworthiness, we want to have like trustworthy answers. So by trustworthy, we chose to go with this meaning that if you can verify the answer a model gives you, let's say you have a video and you have a question like, what does the boy in red do as the girl is running away in the back? The answer is stand up, but maybe to make the answer more trustworthy, we can give the time when the boy is standing up. So if the boy stands up between 3.6 to 5.6 seconds, you can go back into the video and quickly just check that segment and see if the answer is correct or not. So that is what we mean in the context of this work. That's what we mean by trustworthy. So we want to ground the evidence of the answer as a timestamp, and this task is called grounded video question answering. Uh, to address the of course, data, as I said, annotation of times, like annotation of any sort is, very slow and expensive. And especially for a video annotation task where you need to annotate timestamps of all of these actions, that requires like precise annotation requires watching the whole video carefully. And imagine you have like an hour-long video. You want to go through the whole video and annotate 5-second timestamps. So that is very expensive for anyone. So we operate in a weekly supervised setup where we assume that the ground truth answer is available, but we don't have the labels as like or the timestamps for each answer, even for training. So this is our overall problem setup. We want to do video question answering. We want to ground the answer, but we don't have annotations for those groundings. Uh, so this is, the figure here shows an overview of our work. Basically, we use a video LLM for this work, and I'll describe what changes we make. So one of the changes we make is, using something called a multi-scale connector. A pretty straightforward idea to anyone who is familiar with, video understanding tasks. If you are aware of the slow fast networks, which were proposed in 2019 by Jitendra Malik, they had this idea that you can, look at a video, a network can look at a video at multiple speeds, slow speed and a fast speed. So you can, form something like a global local understanding of the whole video. So we follow a similar approach. If you're familiar, with the video LLMs, you generally have a video encoder, you have a connector, and then the LLM part itself. So in the connector, we introduce this idea of multi scales, which basically means sampling the video frames at different speeds, similar to slow fast networks. We think that grounding is a more fine-grained task, and a simple connector may not be suitable for the grounding task. And because we need to actually localize small timestamps within the video, we need finer representations, and that's what we do for getting better representations as the visual tokens. And then we feed all of those into an LLM, standard video LLM frameworks too. But yeah, this is like a thing which targets the grounding part, architecturally, but we still need to address the lack of temporal labels, right? Which is the main problem which we are trying to solve. Trying to train a network for grounded video question answering without having the groundings as in our training data set. The short answer is that we generate pseudo labels and then we try to refine the pseudo labels. Now, how do we do that? I'll explain it now. So we observe that even before this sort of training, like we use the video llama to a video LLM in this work, and we make these changes and fine tune video llama 2 for this task. We observe that even before any sort of training, the model is a good video captioner at least. So if you ask like what is happening in the video, it will give you a good description of what is happening. So we exploit this to create pseudo labels, and then we train the model. Uh, how do we do that? Is that we take a video, let's say like 3 minutes long. We randomly crop out certain segments from that video. So in this example, you see a dog running on a beach, right? So let's say we crop, these like this part of the video, and we ask the model just based on this cropped segment, what is happening? And the model says the dog is running away from the water, right? Fairly good caption. So from this question answer pair and these randomly generated, start and end times, we can generate pseudo labels of two types. One is what we call a referring question, where you refer to a timestamp within a video. So what happens in 65 to 79 seconds? The answer is the model's previous prediction. A dog is running away from the water. And then the second is a more grounding related question. So locate the scene where a dog is running away from the water. The answer is 65 to 79. We can, from these random start and end times and this question, video caption, we can generate these two kind of pseudo labels. And then we can train the model on these pseudo labels. We call this stage two training. I'll go over what multiple stages are, but for now, keep in mind that this is how we can create pseudo labels and we can train the model on those pseudo labels. However, these pseudo labels are not sufficient at all. Like recall that the downstream task is grounded video question answering. So there is no question answering involved in the kind of labels we generated in the previous slide. Uh, we have like sure the model is a good video captioner and maybe now it can ground events, but this does not translate directly to joint question answering and grounding, right? However, and moreover, like so these pseudo labels which we generated previously, they may be noisy because we just use like random start and end times. We randomly cropped out the video. So it's possible that a dog running away from the water may be happening in some other part of the video too, which we did not, which we just ignored because we cropped it. Or maybe within the cropped segment, multiple actions were happening, but the model video captioning model just picked up on one of these. So, these pseudo labels are noisy. That's why they're called pseudo labels. And, even empirically, when we observe, when we train the models on this stage two data, we observe that it does not perform very well on the final joint question answering plus grounding task. So, how do we overcome this problem? We come up with a consistency framework, which basically means that you ask the same question to the model in different forms and check for consistency within the answers. So here's an example. Uh, this is a question from the training set, right? How did the dog react to the coming waves? Recall that we are in a weekly supervised setup, which means that we have the ground truth answer, but not the start and end time of the answer. So we have the ground truth answer, which we can train the model on. So that is run away, for example. And you know, we take the model which was trained on those noisy pseudo labels, and we ask the model the same question. It comes up with some question and some potentially noisy timestamp. So maybe it comes up with the right answer, which is runaway, and some timestamp 60 to 72. We take this predicted timestamp and create a modified question to ask the same model again. So what happens in 60 to 72? If the model says that the dog runs away, so then it matches, like the answer matches the model's previous response as well as the ground truth. So if all of these three match, Then there is consistency within the model's responses. And then we assume that, this timestamp which the model said, predicted earlier, 60 to 72, it is more likely to be an accurate representation, within the whole video. So it might be a good quality timestamp. And if that's the case, we save this timestamp as part of our training set. If any of these three responses is different from the other two, if the model is not consistent, or if the model is consistent but not accurate, so it's different from the ground truth answer, then we discard the timestamp. And this we do for all the questions and all the videos in the training set. So consistency is more of a filtering method, where you, for each question and video pair, you ask the model the same question in different forms. And if the model is consistent, you save the answer. If the model is not consistent, you just discard the answer. And this is how we filter the training set of the training set. And eventually, like, we end up with around 25 to 35% of the model responses, depending on the data set. And eventually, like, as the next stage, which we call stage three, we train the model on these filtered, reduced training sets with these timestamps, which we have filtered. So we think that they are good quality timestamps. So this is the overall of the multi-stage training framework. Just zooming out to give you an overview. Uh, as I said, stage one is the vision language connector alignment, which we have not done. We just take the Video Llama 2 off-the-shelf model, which has already done this stage. So not that interesting in the context of this work. Stage two is where we generate these noisy pseudo labels, and we train a model on these noisy pseudo labels. So we take the models trained from stage one, we use it to generate stage two labels, and again train on the stage two labels. And then stage three, we take the model from stage two, we refine the pseudo labels in our training set using consistency, and again train on these. Now, this is the overall pipeline of training. And we end up with a model which can perform quite well compared to previous approaches. And here are some qualitative examples. Because we work with like a video LLM framework, and we, as I said earlier, we aim to generate open-ended answers. The model can actually generate, these highlighted in blue examples. The model can actually generate answers which are different from the ground truth syntactically, but they mean the same. For example, like put into his mouth and eat are basically the same thing, but they look different. So and like these are some visualizations of how well the model is able to ground the evidence compared to the ground truth, and we see that it like achieves good alignment, at least in these examples. So yeah, this was a really quick overview. I plan to talk about one more work, but if you want any details and want to go over the experiments and actual results, you can look at the paper. Quick overview of the limitations of this work. We focus on single turn conversations here, and recent works on LLMs and video LLMs, they have all moved on to right now multi-turn conversations, where you can keep asking question one after the other. So even in the context of grounding, maybe multiple queries asked together can help the model understand the overall temporal coherence of the video, and maybe that can help grounding better. But yeah, that we focus on singleton conversation in this work. And a related thing, but we only predicted a single timestamp for each query. Actions, can occur multiple times, so the boy can get up and fall down multiple times within the same video. The current consistency framework does not support that directly, at least. So this was the case where so I discussed this work in the context where labels were missing. Now, what about, some uh, different pillars of AI which are missing? So let me discuss one work where the model is corrupted, or maybe the model was not trained enough on diverse enough data. So maybe it did not, acquire complete knowledge perfectly. So this is the second work which I want to discuss. It's called polysemantic dropout. It's conformal out-of-domain detection for specialized LLMs. So a quick motivating example, imagine that you have a cooking expert LLM called Gourmet Chef. If you ask it a cooking related question like what's the proper technique for making a French hollandaise sauce, it will give you a very nice answer, all cooking related, terms. Add the warm butter, ensure proteins don't curdle, and yeah, it because it's trained on cooking specific data, it can give you a nice answer on these queries. But if you ask it a out of domain question, like a plumbing related question, how do I fix a leaky kitchen faucet? It is likely that it will hallucinate and come up with more cooking related responses. It might start well, but no, maybe it can say something like make a solution of white wine and use the gelatin based sealant and let it set for 2 3 hours, because this is a fictitious example, to be clear. But we all know that hallucinations are confident hallucinations are pretty common in LLMs, especially when they are not an expert on the kind of query you are asking. And while the previous one was a humorous fictitious example, this problem is disastrous on safety critical applications like healthcare or finance, or everywhere, every domain where a wrong answer costs a lot. So we wanted to experiment with one of these domains, so we picked healthcare. So we tried to detect these hallucinations of out of domain inputs on healthcare data, and that is where the pillar of AI missing comes in. So if the model has incomplete knowledge about some domain, let's say like mental health domain, and if you ask it a mental health related question, rather than letting it hallucinate, you should be able to detect those hallucinations and stop the model from answering, rather than giving it a wrong answer, giving the patient a wrong answer. So we targeted this problem, and to understand what we did, it I'll just quickly go over what has been done previously. We need to understand this concept of polysemanticity in deep learning. So yeah, LLMs, or any deep neural networks in general, they store a very large number of concepts. A concept is a vague term. Concept can mean idea or an object or a place or anything. Like a dog or a cat is a concept. The United States of America is also a concept. So basically, they store a very large number of concepts or ideas, and the number of concepts they store is far greater than the number of neurons they have. So the previous research has shown that uh, all networks, but especially LLMs, they are polysemantic in nature, which is shown by the middle part here, which means that each concept or each idea is represented by a combination of multiple neurons, as opposed to maybe a monosemantic code where each idea is represented just by one neuron in one layer. LLMs and deep learning networks, they are inherently polysemantic, and because of this polysemantic nature, they are redundant. They have like redundant representations, and that makes them robust to feature perturbations. If you randomly corrupt some features, or if you randomly drop out some neurons within the LLM, they are more likely to be robust because of this polysemanticity. And can we use this idea? So can we use the polysemantic nature of the model to detect its confidence, or detect out of domain queries? So we asked this question in this work, that how much disturbance or how much dropout can we introduce before breaking the model? So recall that models are inherently robust because of polysemantic nature, but like how robust are they? How much dropout or how much disturbance can we introduce before breaking the response? And the hypothesis is why this is relevant for out of domain detection is that in domain inputs, if a model is trained on cooking data and you ask it a cooking related query, that will be an in domain input. So that will have a robust representation within the internal layers. So a lot of neurons will be representing that concept. Uh, so it will be more robust to disturbances like dropout. However, out of domain inputs which have brittle representations, they might have lower dropout tolerance. So they like the response will break quicker if we keep on increasing dropout for out of domain inputs. And to check this hypothesis, like we propose this framework of iterative dropout within LLMs. Basically, what I described earlier, put together into a framework which we can implement. Um, so we ask, like, given a medicine expert, let's say like ophthalmology expert LLM, we ask it some query, and we ask it without any dropout, without any disturbance, we get some response, which is the original response shown in blue. uh, we introduce some amount of dropout. We again get a response. We keep on increasing the dropout until we get a response which is different in meaning from the blue response. So that is like this red box here. And we measure the amount of dropout which we needed to break the response. Essentially, breaking means change the meaning of the response compared to the original. And we measure the amount of dropout which we needed to introduce, and we calculate, this this scalar value alpha, which is called a non-conformity measure. Basically, it measures, how abnormal a query is. So if you have like an in-domain query, which would have a higher dropout tolerance, you would have a lower alpha because dropout tolerance is higher, alpha becomes lesser, the nature of this formula, and that's why we call alpha non-conformity measure. Uh, this actually is kind of standard in anomaly detection task, and we frame this in an anomaly detection problem. So given a distribution of alphas across different samples of in-domain and out-of-domain, you will see like different peaks in the distribution where you know uh, in-domain has lower alpha and out-of-domain has higher alpha. And basically that's what we utilize to distinguish between in-domain and out-of-domain inputs. The exact details and the exact mathematical framework which we use, that's called like ICAD, but I think that's out of the scope of this talk. Considering the time we have, I'll probably skip through it. You can go through the paper for more details. But basically, the idea is you have a different distribution of dropout tolerance, or like this alpha scalar, and you can, based on, given a new query, whatever alpha you get by doing this iterative dropout process, you can compare it to the distribution and get a good prediction of whether the query is in domain or out of domain. Uh, One more idea I want to talk about is what I discussed in the previous slide. That is only applicable to one layer. Like it is only like the framework is consistent only if you introduce dropout in one layer. However, we have a lot of layers, like in like modern, even 7 billion LLMs have as much as like 32 or 48 layers. So we can actually do this experiment across multiple layers and ensemble the predictions, which is what we do in our final method to get a more robust predictions. Basically, you can perform this process independently across multiple layers, and then you would get multiple probability values when you compare the alphas to the probability distribution you have, and then you can aggregate those probability values by taking different methods. Like you can take a mean, you can take harmonic mean, you can take the minimum, you can take voting aggregation, you can make multiple layers vote for a prediction like in domain or out of domain. And we experiment with multiple different modes of aggregation. We find that the mean is the best and the most stable. But yeah, the idea is you can ensemble predictions across different layers too. These are some results as plots. So we can like these are AUROC curves. So the higher up and more towards the left a curve is, the better. And we observe that our method is performing significantly better than the baselines for the out of domain detection task. We also like plot the false alarm rates compared to the threshold epsilon. That is a bit more technical, related to how we use the ICAT framework for anomaly detection. But basically, we see that the false alarm rate is usually below a guaranteed theoretical threshold, which the framework gives. But yeah, these are some results. And so, to conclude here, at least in this work, we propose a novel conformal out-of-domain detection method using the iterative dropout framework and dropout tolerance ideas. We hypothesize that current networks would have like different behaviors for in-domain and out-of-domain inputs, and we are able to exploit that to detect out-of-domain queries at inference time without training any additional network or even fine-tuning the LLM. For future work, like this could potentially be used with other classes of models like multimodal LLMs. And like we only tested with medical applications, but this could be applicable to, other sensitive domains like, security, even sports or finance, even the cooking related example which I had discussed earlier. So yeah, with that, I would be ready to take questions.